Thanks, Natesh. Very interesting constrained sampling problem. The next speaker is going to be Panos Toulis from the University of Chicago Booth School of Business. Do we have Panos online?
Yep.
I think you're muted.
Can you hear me?
I'm kidding. I'm kidding. All right. Panos, all you. Thank you. Thanks for being here.
Okay. Let's see. I cannot see my slides though. If
That's a bane of our existence.
I can see myself twice. All right, there it is. Thank you so much. So hi everybody. I'm very sorry not to be there. Unfortunately, my flight was delayed severely for many hours, very early today. So I'll have to work with that. So I'll do my best. And it is what it is. So today, what I want to talk about is a problem that relates to identification of periodicity. And that's, I think, a pretty foundational problem for finance, for astronomy, and other fields. Actually, today, kind of in line with Natesh's, let's say, exploration of similarities with other fields, like finance with other fields, I'll do something very similar. I'll try to talk about identification of periodicity in astronomy specifically. But specifically in the context of exoplanet detection, which is it's a very recent, a very exciting area in astronomy. But the underlying problem is a statistical one, which is the estimation of identification of periodicity, and it has obvious applications in finance as well. In doing so, I will talk about also structured inference, which is I call it structured inference, but you can think of it as a third way of doing inference beyond Bayesian statistics and beyond also asymptotic frequencies. So let's jump right into it. And next slide, please. So I'll start with an early cool example of that question of whether there's periodicity in the data or not. And one of the earliest examples is the question of whether the extinctions on Earth are periodic. What you can see on the bottom right are data. On the y-axis, there are biomass extinctions. On the x-axis, there's time. And so the question is whether in this data there's some periodicity. And in that paper, in this very famous paper, the authors figured out that they argued that there's a 30 million roughly periodicity in extinctions. And actually, there is some theory that is backing that up. One theory says, astronomical theory says, that there's actually a second sun in our solar system that it's hidden from us for like millions of years, but periodically shows up again. It attracts mass from the Kuiper belt and kind of throws it towards the direction of Earth. So it's a pretty catastrophic scenario if that's true, obviously. So it's very important. It's obviously a very important question, even though it's a long-term important question. Still, it's a very interesting problem, right? Whether these time series that we have collected here have an underlying periodicity. Now, the method in that paper was pretty heuristic, and it was contested early. And today, I'm going to describe the methodology that also contests that that finding, perhaps with a more rigorous, method. Next slide, please. So the estimation of periodicity in general is a very fundamental task because it kind of shows up in finance, it shows up in ecology, climate science, it shows up in astronomy. And today, my main motivation, my main example is going to be exoplanet detection, like it will be in astronomy and a problem that is coming from astronomy. However, the underlying problem is a foundational one in time series, but is a deceptively simple one. You might say, I can have a model. I know how to fit periodic regressors, right? So just I can have period as my independent variable. So I can just fit it and then try to kind of look into the, let's say, the maximum likelihood as my estimate for periodicity. However, this method does not work because, first of all, it requires assumptions of the observation times being IID. And second is it requires that your assumptions, requires this regularity assumptions of your maximum likelihood, for instance, being regular, right? Like being consistent, being hopefully asymptotically normal, and so on and so forth. Now, this specific problem is very far from regularity. It's very far from standard theory, and I will offer some more details going forward. Two very specific problems are, one is that in many cases, observation times exhibit patterns. They're not IID. And we're very familiar with making that assumption, and it's very, very, very hard to kind of part away with that assumption, right? That your data are IID. But here we have to do so because there are some important physical constraints. In astronomy, for instance, you cannot make observations. We usually make observations during the summer. It also has to happen during the night. And so these very strong periodicities in the data collection, they imprint periodicities, spurious, if you will, on the data themselves. That's a more general problem, like that goes back to the biased sampling mechanisms with work of Rubin, Little, and so on and so forth, where you have to think about how your data are collected, and if there's some bias in how the data are collected, this is going to show up in your modeling phase. So you have to be careful about that. And here is a very striking example of that effect. And the second problem is that the assumptions of consistency are not there. They're not realistic. So our estimators are going to be, in many cases, not consistent or cannot be considered to be consistent, at least. And also they deviate a lot from normality. And I'll show you examples of that. And in these cases, it's unclear how to proceed with inference. Next slide, please. So how you can proceed here? Well, the standard method is either asymptotic frequencies. So you say you have a parameter to estimate theta star, and then you say, let me take the maximum likelihood and try to understand how this varies around the truth. That's one. The other is a Bayesian approach, where you say I have the data. Let me try to kind of attach some probability into my parameters, and let me explore that space, right? This posterior distribution. However, both of these methods, they do rely on asymptotics. They do rely on some regular likelihood, like perhaps normal even. And even more crucially, there's an assumption of an identifiability, an assumption that we can identify theta star that in many cases it's not there. And this will be an example. The exoplanet detection is going to be an example of that. And today, what I'm going to describe is, in talking about this exoplanet detection application, I'm going to talk about the so-called third way of doing inference. I call it structured way of doing inference, but that's perhaps not the best way to describe it. But on a high level, what is going to happen is that we're not going to rely on asymptotic normality or any other sorts of asymptotics. We're going to rely on some structural assumptions on the data. Let's say some invariances, some symmetries. And so given that, we're going to establish a methodology that is going to revolve around these symmetries. And this methodology kind of relates very closely to the so-called randomization tests from statistics. Okay. Why do we have to do that? First of all, because we can use this method under non-IID assumptions, non-regular assumptions. That's one. And second is that this approach will be finite sample valid, or at least will have very good finite sample performance, better than the other standard approaches. I'm going to focus today on periodicity estimation, but I have all other applications in mind as well. If there is time, I can discuss about them as well later. Okay, so next slide, please. So a few words about this exoplanet detection. This method is the method that I'm going to describe today is motivated by that problem. This project is in collaboration with Jacob Bean, who is at the Department of Astrophysics here at U Chicago. And the exoplanet detection is a fascinating new problem where we kind of look into stars essentially, and we try to figure out whether they're exoplanets, planets revolving around the star. The first detection was for 51 Pegasi b, and it was a groundbreaking observation and discovery that was awarded the Nobel Prize in Physics in 2019. And since then, there have been amazing discoveries, even a few years ago, and even in our immediate stellar neighborhood, which is the Alpha, the Centauri system. And this is amazing because if there are exoplanets in the immediate neighborhood, then it means that they're ubiquitous, and so that kind of changes completely our picture of the cosmos and what's in it. Now, I should say though that even though the earlier discoveries have been confirmed with other means as well, The most recent discoveries are still non fully confirmed, and so we kind of contribute to that as well. And that's important because false discoveries are not uncommon, as I'm going to argue very soon. Next slide, please. So a few words about how this works on a very high level, because I don't understand the very specific details. But on a high level, what is going on is that, as you can see here in the picture, there's a star out there, kind of very far away. It can be millions of lights of years away, lights of years away, or thousands of lights of years away, or even more. And then there's an exoplanet revolving around the star. And the fact that this exoplanet revolves around the star creates a gravitational seesaw. So that basically kind of induces some jitter in the movement of that star. So that jitter affects the light that's being emitted from that star, from the Doppler effect, essentially. And so on Earth, what we see is basically some oscillation in the spectrum of the light coming from that star. So essentially, this oscillation, if we discover an oscillation in that light, essentially this means an exoplanet discovery, right? There are other nuisance signals that might be there. Let's say the rotation of the star and other things that create that same effect. But we can control for those, and then what is left is that jitter. If there's some significant jitter that is left, then this can be attributed to an exoplanet. Actually, that same signature is what Jupiter, like this large planet in our solar system, imprints onto our sun. So if someone, like some aliens kind of are observing us, are kind of using the same method, they could detect the presence of planets just by the effect of Jupiter on the sun. So this method is astonishingly simple, but also astonishingly successful and smart, because basically you have to only observe the location or the velocity of the star, the so-called radial velocity, which is the velocity of the star with respect to Earth. So you just kind of observe that radial velocity, and from that we're able to detect the fingerprints of an exoplanet around the star. So so there are two main steps in that process. First of all, you detect if there's any periodicity, then you try to estimate it, like what the exact value of that periodicity, if detection was successful. Next slide, please. So this is our setup, very simple. TIs are going to be our observation times, and then YIs are going to be the radial velocity measurements. Again, radial velocity means the velocity of a star with respect to Earth, like as an Earth observer will record it. The differences between those observations, these successive observations, I'm going to call them spacings of these observation times. And then the probability distribution over this observation times is the observation design, okay? And there are some inherent biases, some physical constraints in these observation designs. They cannot be IID, right? Because we have to observe during the summer, we have to observe during the night. And also, if we're interested in a specific star, we have to observe it at the time, usually when it's at its peak, at zenith. So there are many physical constraints that go into these observations, and standard theory does not account for that. Standard theory usually assumes that observations are unconstrained and they are IID and so on and so forth. Okay. These deterministic patterns here, specifically in this application, they do induce some signals that are very strong and very highly can create some nuisance. For instance, the signals of one-day periodicities, if we see them in the data, it's unclear of whether it's an exoplanet revolving in one-day period, or it's really our observation times that just happen every night, and that's why they induce one-day periodicity. So we have to be careful of that. That identification is not here now that easy. Okay, so next slide, please. So T's are going to be our times, Y's are radial velocity observations. Now, how do we proceed? What is the standard process here? Well, first of all, we just write down a regression model, simple additive model usually. YP is going to be our periodic component, and this can be cosines, sines, or other types of terms that induce periodicity, or model periodicity. Theta star is our unknown period, just a number, okay, measured in days. And psi star, as you can see there, is basically nuisance parameters. It can be regression coefficients or anything related, okay, to this periodic component. And then we also have an error component. Now, how do we proceed here? Well, we have the so-called generalized lob scramble periodogram, which is kind of very widely used for these types of applications, and also in cases where the spacings are really irregular, which are complex problems for time series. What do we do? Essentially, we kind of set up, if you will, an F statistic, right? Or like a model deviance statistics, where we compare the model fits when there's no periodicity and the model fit when there is periodicity, assuming periodicity. And so that parallelogram value, as we say, is going to be large when the model fit under periodicity is much better than the baseline fit. Okay, so graphically, how this looks like is, can we go on the next slide, please? Is the so-called periodogram. On the x-axis, you have periods, usually in the log scale. On the y-axis, you have that periodogram value. You can think of this also as the likelihood value, right? It's proportional to that. So the higher the peak, the higher the likelihood from a frequency perspective of that specific period. And so the peak, for instance, in that periodogram is also the MLE, like the maximum likelihood estimator for your period. And so usually most of the methods, kind of going back to Fisher, they do rely on the periodogram peak. The methods for detection, not estimation yet, just for detection of periodicity. They do rely on that periodogram peak, like the value of the period that maximizes that model fit. Okay. Now, detection of periodicity is very simple, not simple, but very straightforward. Like you can say that you can attach significance to it. Fisher was the first to derive test statistics that could be used to detect the null, to test the null of no periodicity. He figured out the exact distributions under some normality assumptions, etc. Now we can do other things like bootstrap and other things where we can also incorporate non-normal errors. So that problem is solved. The detection problem is solved. But the question is, now the inference question is more complicated. And actually, you can see what the problems are, right? Since this periodogram here is essentially likelihood, you can see now that our likelihood is highly irregular, has many peaks, is multimodal, and so there are many things can go wrong here, because standard methods usually assume that your likelihood is regular, it's smooth, hopefully unimodal, so things kind of look nice. But here the likelihood is just very irregular, and that creates all sorts of problems for inference. Next slide, please. So just to be more concrete here, a common mistake done by standard methodology is that they kind of interpret the detection of periodicity. They conflate. Sorry, the better way to say this is that they conflate the detection of periodicity with estimating periodicity, the inference of periodicity. So the underlying assumption, the subtlety here in the underlying assumption is that theta star, the true value, has to be near the peak, right? And that's usually a mistake or like a bias that I think everybody has, right? Like when we feed our models, we tend to think that the truth has to be near the peak of our likelihood, but that's not guaranteed in every application, right? In many cases, especially in this one, we can be very far away. And that's because the consistency assumptions are not necessarily met, right? So here specifically, we have three problems. One is that, as I mentioned before, the likelihood is irregular, is non-smooth, is multimodal. And so we cannot assume that the sample distribution of that peak is going to be around the truth, or is going to be normal, or even has to be continuous, right? It can be some very weird shape, mixture, anything, right? So all of the standard statistics here, assumptions kind of are thrown out of the window. The other problem is that the observation times are not random, and so not even consistency is guaranteed, let alone normality. Not even consistency is guaranteed here. And for consistency, usually a theoretical assumption is the so-called separability of those modes. So separability means that as you get more and more data, those modes are going to get separated, and going to be separated more and more, and the truth is going to have the highest peak, right? The highest peak is going to correspond to the highest. The highest peak is going to correspond to the truth. But here, this is not guaranteed because our observation times are not IID; they're not random. They might be completely deterministic. Okay, so that's a big problem because we're not guaranteed to have even a consistent estimator. And finally, another problem here is that the errors are assumed to be normal usually, and that's how theory kind of proceeds. But we might want to be robust to that, right? We might want to have more heavy-tailed errors, non-normal, etc. So these three problems are very important problems for standard methods, and they cannot really address them. The frequentist asymptotics, or even Bayesian methods. And for Bayesian methods, the discussion might be longer, but on a high level, what Bayesian methods can do is something even worse, where by applying some priors there, uniform priors, you might bulldoze over those peaks, right? Those problematic areas, those areas that give you identification problems. So by using Bayesian methods, you might basically hide the identification problem under the rug, because these uniform priors are not really doing what we think they do, right? They kind of, in this case, they kind of obfuscate the issue. Next slide, please. Here's a very simple example where this simulation setup is, we have IID observations even, we do have uniformly distributed errors, we have normal IID errors, still though we do have identification issues. With this data now, you see that on the left, the periodogram is actually quite misleading, because the true value is not exactly at the peak. You see multiple peaks there. This is the identification problem in statistics, or aliasing problems in engineering and signal processing. On the right, you also see the nightmare scenario for statisticians, where you have, this is really the sampling distribution of your periodogram peak, which is, as you can see, usually we assume this is normal around the truth, and we only care to know the standard errors, right? This is how standard inference proceeds. But here, the sample distribution is very far from being normal. Actually, you see it has only 3 peaks and just only 3 peaks. So normality here will kind of be very bad assumption to work with. So definitely we need something different, right? A different way of doing inference here. Next slide, please. So how do we proceed? Let's start with a very simple problem first, and then I'll try to make it more practical. I'll start with an impractical problem, a simple impractical problem, and then I'll try to make it practical. So the impractical problem, it's the so-called, we can think of it as a global null hypothesis, where suppose we want to test a null hypothesis where the true period is equal to some value theta 0, and then the true nuisance parameters are equal to some value psi 0. Okay, so essentially the null hypothesis here assumes everything about my model, about the model parameters. So in this case, I want to tell you that describe an exact test that is possible. And by exact, we mean a test that is not going to rely on normality, and is not going to rely on irregular likelihoods, and is not going to rely on n being large. So it's going to be exact. That's what I mean by exact method. So we're robust to all of those assumptions that are assumed in standard methods. So how do you proceed with that simple null hypothesis? Well, given the null hypothesis, immediately you know the model parameters, right? You know the period, you know these regression coefficients. So immediately you can impute, as you can see in the first one, you can impute the periodic component of that regression. Okay. Then when you have that component, then you can subtract from the actual data, and you can get the imputed errors. Now you know the errors exactly. Okay. And then what can you do? The moment you know the errors, you can actually make an assumption on some symmetry on those errors. Not necessarily normality, but you could assume, for instance, that the errors are sign symmetric. Not even extensible, just sign symmetric, right? It means that they might be, if you change their signs, they have the same distribution, okay? Or sign invariant. So you take these errors and then you kind of flip their signs at random, essentially. Now you have a new set of errors. You kind of add into the original periodic component, and now you have a new data set. Okay, and now you have a test statistic, which could be the periodogram peak or some other version of that, some other summary of that periodogram, and then you compare your randomization values with what you actually observe in the data, and that's a valid you get a valid p-value for your null hypothesis. Okay. Now, that method again is exact, because here I'm invoking no assumption about the errors except for the some sign symmetry, which is a much weaker assumption than, let's say, IID normality. And two, I don't require it's also finite sample, because I'm not using anything about the anything. I'm not making any limit argument, right? This method gives you a valid p-value for any finite n. Okay. Next slide, please. So using that method, you can also get confidence sets for your unknown period. Now, because your psi star is a nuisance parameter and that global null is a strong null, what you can do is you can construct intervals where for every period value that you want to test, you can take that p-value function and then maximize it with respect to this unknown, to this nuisance parameter. Okay, that's something actually you can do by simply for a given period running least squares on your psi parameters, and then calculate the p-value and then test whether that p-value exceeds or not the alpha. And this is how you construct confidence sets, not confidence intervals, because they don't have to be contiguous, but confidence sets. Okay. And so equation 1 to equation 2 give you some ideas about how you can construct that. Just in the interest of time, I will just skip that for now. Just know that what we're doing here is, first of all, we're just scanning all the possible periods, and 2, we're just maximizing over that p-value calculation that I described to you earlier. Okay, so what you probably notice here is that we're doing a lot of computation. That's something I will describe. Next. But using that method, you can construct valid confidence sets. Next slide, please. Okay. So before I give you concrete practical applications and results, some quick discussion about the what's good and bad about this method. So again, just to summarize the goods. So this method is finite sample valid in its best form, right? When you try to maximize over these nuisance parameters, then it gets complicated. But you can use least squares in that case because now the likelihood becomes regular the moment you condition on the period. So there are some technical details here that kind of work out. In any case, this method is finite sample exact when it's exactly implemented. When it's approximately implemented, it's approximately so, or in the limit is finite. It's not finite sample valid, but in the limit it kind of works is valid. But it also performs well in finite samples, even the approximate one. We make no assumption about the test statistic. It doesn't have to be well behaved. It doesn't have to be normal. That doesn't have to have continuous null distributions and so on and so forth. So that's quite liberating. We make no assumptions about the observation design. It doesn't have to be IED. We make no assumption of normality on the errors. And we also kind of condition some other hyperparameters that are kind of important technical details for when we do optimization, but let's not discuss this right now. However, what are the challenges? There's no freelance, right? So what is the there's no freelance here. So what are we losing? First of all, the method will be conservative. How to use it, choose a test statistic, and also the most important one is computation. So what we're doing here is that essentially we're trading assumptions with more computation. But I think in the modern era, that's fine, right? Because we do have lots of computing power, supercomputing clusters that we can use to trade off assumptions and robustness for just more computation. I think that's a trade I'm willing to make. So okay, so now we can kind of move on to some practical application just to show you what you get out of it. So this is now what you get out of this method. Like that table you see over here on the right, this is the output of our method. So we see that that column for these candidate periods, we can derive a p-value, and then if that p-value is small, we can reject that period. If it's large, then we can accept it. So just for convenience, I tell you also the 95% interval, not intervals, confidence sets, and then 99% confidence sets. When you see a yes there, it means that value of that candidate value of the period cannot be rejected. So what happens here in that simulation example, you can see that our method is not getting tricked, right? You can see that it has values of 0.5 days or like 0.77, 1.41, that's the true, and 3.41 cannot be rejected. So all of them are in the confidence set. But these are the 4 distinct values, right? This is not an interval between 0.5 and 3.4. These are 4 distinct values that cannot be rejected. So the method is also quite precise in that respect. Okay, next slide, please. Specifically now for this exoplanet applications, 51 pegacb is a good example, ground truth example, because we know the ground truth here. And here's an example where you see this likelihood being irregular, perhaps having identification issues, but actually the signal is quite strong. Using that method again, we cannot reject only the 4.23 signal, which is the actual kind of official reported period for 51 Pegasi to be that exoplanet. All the other values that are perhaps kind of near 1, let's say here, that could be, you can see those peaks there, those other peaks are being rejected. So that's good. It kind of shows you that the method is not too conservative in practice. Next slide, please. Here's another exoplanet that's also confirmed, Gliese 436b. Same idea here. Despite having those peaks, despite having more volatility there, more variation compared to the periodogram before, still we have very exact inference here. 2.64 is the official period day for that exoplanet, and has been confirmed with other methods as well. Now let's go to more recent discoveries, and this is perhaps more interesting because this has not been confirmed, and these are still up for debate. So next slide, please. So there was a paper in Nature a couple of years ago about the discovery in Alpha Centauri B, and you can see the periodogram on the left. What happens here is that in Alpha Centauri B is kind of in our immediate stellar neighborhood. It's the closest. Let's say the closest star, like 3 stars in that system. Now, what's happening here, as you can see on the right, the 99% confidence set includes many different candidate period values. Even more concerningly, the period values around 1 day cannot be rejected. So it's very likely that this signal, this discovery, is spurious. That there's not enough evidence. Or at least there's not enough evidence to declare significance yet. There's many values here that are are consistent with the data. And I should kind of emphasize again that the method that we're applying here is able to discover that because it is able to discover this identification issue again because we don't assume that likelihood to be regular, whereas other methods assume that the likelihood is regular, and that's why you can easily get tricked and kind of determine significance around the peak when there's none. And final example, next slide, please. Again, a discovery on our immediate neighborhood on the Centauri. Proxima Centauri is the third part of that system, on the 3-star system. Well, here the situation is better because the authors reported, again, it's a Nature discovery, kind of reported in Nature. The discovery is at 11 days. That's the reported period, which is in our confidence set. In our confidence set, however, there's another signal that's at around 0.9164. It is rejected. It is not rejected at the 1% level. It is rejected at 5%. So technically speaking, we will not declare a complete discovery. But talking to experts, it seems that this is not too concerning. That experts will think that that discovery is real, and that nuisance signal at 0.9164 shouldn't be too much worrying. So you kind of get like a full spectrum, let's say, of results here, right? We got positive results for known cases, we got negative results for debatable cases, open cases, and then another result that kind of looks negative but weakly so, like experts saying that still this is not like powerful refutation in any way. So yeah, that's all I had for today. Thanks for your attention. I will be happy to take any questions. If there are any other questions about the application of this method in other problems, I'm happy to discuss. I have another application, COVID estimation of COVID prevalence. Happy to discuss that as well. So thanks for your attention, and sorry not to be there.